Okay, everyone, welcome to our fifth webinar. This is Sam Stambula from the Canadian Centre for Electron Microscopy. I'm our outreach coordinator here. So today we will be presenting on scanning transmission electron microscopy, looking at just an introduction and some imaging modes that you can do when working in STEM. And our presenter today is Natalie Hamada. She is one of our Titan operators at the center. So just before she begins, I would like to remind you, if you have any questions, to please put them in the chat. I will be collecting the questions throughout the presentation, so as a question comes up, you can just throw it in the chat. You don't have to wait until the end of the presentation. And I will collect those, and then we will be able to ask Natalie a few of them at the end of the webinar. And any questions that do not get answered, we will be putting those answers up later on. So this webinar is also being recorded. So the recording of this webinar and all previous webinars and any online workshops that we have can be found on our YouTube channel, and you will see the link for those in the emails that I will be sending out after this. So Natalie, that's all the announcements. If you're ready, feel free to start.
All right, thanks, Sam. Can everyone hear me?
Yes, your sound is good.
Great. Okay, cool. Well, thank you again, everyone, for joining us today. As Sam said, I'll be discussing scanning transmission electron microscopy. I'll just be giving a little introduction and to the microscope and talking about imaging modes. So, here we go. A brief outline. I'll be discussing, what is STEM, and contrast it with TEM. Talk about the lens arrangements in our Titan system, and then I'll end it with a discussion of STEM detectors and acquiring images in TIA. Just to make a disclaimer, I'm in no way promoting, any one microscope or system. This is just what we use here in our facility. So I'm just going to be talking about the TEM or STEM in terms of that. I arranged this presentation to be a more practical kind of talk, as it seems that a lot of our users would like to have a better understanding of how our specific microscopes in the facility work. So keep in mind that each microscope is different, such as if you're working on a dedicated STEM instrument, but nonetheless, the general ideas still apply. So just to start to, here's a few textbooks of that I found quite useful. They're pretty popular. I'm sure you might have heard some of these already, like those Pennycock and Nellis ones, the Williams and Carter, and the Ernie ones. I'm also putting up here the Titan condenser manual, as I find its reading manuals are quite helpful, and it's a great supplement to text, as they can go on only so far in terms of practical application. So when you're, these different microscopes can use different lenses and detectors settings. So reading manuals is quite helpful. And here at the CCM, we have 4 TEMs. One of them is not shown. We acquired 2 Talos right before the shutdown, and in fact, now this makes our aberrated corrected Titans the oldest TEMs in our facility. All of these TEMs can be operated in TEM and STEM mode, and they have an array of add-ons that could be used for probably a technique that you're interested in. So if you like the specifics of all the bells and whistles that we have on these microscopes, please feel free to visit our website shown here. We can do a lot of like EDS and EOS, bright field, dark field imaging, TEM, high resolution STEM, a bunch of different techniques. So they're all listed on our website. And TEMs make up only a fraction of the available instruments that we have in the facility, or in general used for characterization of your material. So which begs the question of why use a TEM? Well, first of all, I could say it's a really cool instrument. I mean, as you can see, it's validated by Obama's excitement in his face, as you can kind of see here. He's using an aberrated corrected Titan. And this wasn't taken out of facility, but at a facility in Oregon, but nonetheless, still cool. But if that doesn't convince you, then why you should use TEM? Then maybe I can show you this image on the right here and say that we can use STEM to obtain high resolution images and correlate it with spectroscopy data using these microscopes. So we can get imaging and spectroscopy and mainly, but we can use it for a bunch of other techniques as well. So one thing is that using electrons, they're unique in that we can use a charged particle to probe our matter of interest. So from this, we can get a whole slew of information by taking advantage of the wave-particle duality of these particles and their relationship with matter. Another little promotion here, if you're only partially convinced of why you should use TEM or would like to learn more about the basics of the TEM, I recommend watching one of our webinars from a couple weeks ago in which a bunch of TEM techniques was discussed. And this can be found on our YouTube page, along with other webinars presented in this series. So, okay, back to science. So as with any experimental design, it's useful to ask some questions before jumping right into a technique. So in terms of considering the TEM, some questions you could ask yourself might be, what information do I hope to gain? Am I looking to image atomic defects or dislocations? Am I looking to get elements of composition, crystallinity information about the sample, and so on? So from this, you can kind of ask yourself, well, then what kind of contrast am I after? Am I after like mass thickness contrast, diffraction, or phase contrast? And also what kind of resolution do I need? And in some cases, obtaining, really high resolution requires special sample preparation, which could be quite costly in that we might need to make a uniform thin sample using the FIB. So that would kind of increase the time standing between you and some really, really nice data. So you also might want to consider whether your sample is amorphous or crystalline or a bit of both. Is it sensitive? What can and what can it not be exposed to? Since TEMs work with the transmitted electrons at high acceleration voltages, you'll have to keep in mind of the potential damage that could be done to your sample. And this can give you some false representative images. And finally, it's important to know how to interpret your data. Instruments can provide data, but they don't have, the brains to interpret them. So you'll have to factor in some time required for data interpretation, and as you want to make sure that you're extracting every bit of useful and correct information from your data. So nonetheless, STEM is quite useful, and as you probably have seen in lots of literature, it's a quite common technique that is used to characterize materials. We can operate the TEM in STEM mode, which rather than using a parallel beam to illuminate our sample, we converge the beam to a probe and raster across your sample in the X and Y direction. We use electromagnetic lenses to help collimate or focus and demagnify the electron beam onto our sample. And it's very much similar in nature to an SEM, but one major difference being that we're collecting electrons that have been transmitted through your sample at very high speeds and using a high acceleration voltages. So STEM most commonly uses detectors that collect forward scattered electrons to form an image, and almost always can be used in conjunction with some kind of spectroscopy technique, such as that shown in this image here, where we use an energy filter to collect some energy loss spectra. And so from all this, we can get the structure, the chemistry, and the bonding of your sample at very high spatial resolution. So as I said, STEM detectors collect transmitted electrons, and we can describe them in terms of how they're scattered. So as the beam is rastered or point by point across your specimen, the electrons can be forward scattered to these detectors, resulting in contrast in your seen in your image. Here, first off, we have the bright field detectors or the axial detectors, which collect on-axis scattered electrons in addition to the unscattered transmitted electrons. As like matter's mostly, empty space, so a lot of these electrons will just go directly through your sample and actually not interact, having any scattering interactions. These type of bright field detectors produce images that are quite similar to coherent bright field TEM images, shown here in this top row, with one advantage being that we can get an image that isn't subject to aberrations from the image forming lenses as we would use in the parallel beam mode. It is interesting to note that we still see contrast reversal going through focus, so here versus here, which is a factor resulting from the coherent imaging. When we increase the angle of our detection, so collecting more higher scattered electrons, we transfer out to our annular dark field detectors, which collect these off-axis electrons that have been scattered to higher angles relative to the optical axis. These detectors are donut shaped, and so that the on-axis beam is not collected. These high-angled scattered electrons are incoherent in nature, meaning they have no phase relationship with the incident beam of electrons. Thus, we don't see any contrast reversals like that shown here. And so instead, as we change our defocus, the image just gets blurrier. So here I just want to put some, rectangle drawings of our ADF detectors into perspective. This is like the donut-shaped detector itself, and it's constructed so that the outer detection angle is about 6 times larger than the inner collection angle. It's a scintillator made of yttrium aluminum perovskite crystal, and it produces a photon when it's hit with an electron. These photons travel through the quartz cylinder attached to a photomultiplier tube separated by an aluminum shield. An application of the signal from the cathode ray tube is described by a range of grayscales, giving us our grayscale image, as we see here, just grayscale. So one important thing or advantage of using dark field imaging is that you're collecting these incoherently scattered electrons. So they can be quite useful in a way that it simplifies the interpretation of images that you get, as opposed to say looking at a phase contrast or diffraction contrast image that you get from a TEM. So here, if we just kind of consider a layer of atoms here, we can plot the object function, which describes the potential or the probabilities for each of these atoms to scatter electrons at high angles. So i.e. like the scattering cross sections. And these peak heights are approximately proportional to a little less than z squared. So the sharpness in the peaks here indicate that each atom is an independent scatterer. So due to the quantum mechanical view of scattering, we can describe scattering as probabilities. And in fact, the wave function collapses when it actually hits the detector. So this kind of actually means that the actual scattering does not really occur until like the moment of detection. It's kind of still kind of like boggles my mind. But anywho, when a probe comes along, so here, shown here in green, the potential of the scattering is weighted to the probe intensity, and the image can be mathematically described by like the cross correlation of the object function and the magnitude or the intensity profile of the probe. So this definition of incoherent imaging just tells us that the image that we see is a representation of the scattering cross section and the probe. And since the signal is integrated over the entire detector, any phase information in the object is destroyed. Where is my mouse? Okay, there it is. So since there's no phase information, we see no reversal in contrast as we change the focus, defocus, but rather the function decreases, and then as we saw earlier, it just results in a blurry image. Okay. Oh, there we go. Okay, so here we can see an example of Z contrast in comparison with the HRTM image shown here. Here we can clearly see the germanium layer is higher in contrast, so the heavier germanium is heavier than silicon and oxygen, and so they show up as darker in contrast. Additionally, we can see the design of the detector is annular in shape, so we can collect most of the scattered signals, as opposed to dark field team imaging, where we need to isolate a fraction of the scattered beam to produce a dark field image. So we can collect most of the scattered electrons using these annular detectors. So from the cross correlation, we can also deduce that our image resolution is dependent on the probe size. So a finer probe would allow us to collect scattering from a single atom, giving us images similar to that shown here, in which we can see, the adsorption of atomic platinum on titanium dioxide. And lastly, since our images are not formed by objective and projection lenses, the images themselves don't suffer from aberrations in the lenses, or aberrations produced from the lenses. But nonetheless, we do use lenses to demagnify and converge the beam into a probe, and so the probe itself does suffer from aberrations. But luckily, there are aberration correctors that we can use to reach a really small probe size. So when forming an atomic resolution dark field STEM image, it's important to consider your setup of the probe and your detector. So it's also important to note that forming a good image is dependent on your sample, but I'll discuss that a little bit at the end. So first, let's kind of discuss, forming a STEM probe. So overall, the goal here is to demagnify the beam of electrons emitted from the electron source to a point on our specimen. So a beam of electrons emitted from the source gun can have a crossover diameter of about several nanometers. So we'll need to demagnify this source or this image to a point, and we can do so using or in the microscope, the condenser lenses and the objective lens systems. So in the Titan, we have a 3 condenser lens system. The probe is also formed using a C2 aperture, and that helps to find the convergence angle of your beam. And we have here a set of twin objective lenses shown here, in which the upper pole piece is strengthened to converge our beam into a point on our sample. So not just note that I'm not going to be discussing how to align the microscope. There's lots of other things that you'll need to consider, such as stagnation and tilts and pivot points and things. But I'm rather just going to be giving a general discussion of how we form this, how we converge this beam into a probe. So the first step is to you need to demagnify the source image. So that's normally done with a C1 lens. So that's basically choosing your spot size, or this gives you your beam current. So for FEI systems, the smaller the spot size, we see a magnification of the source relative to the higher spot size. So magnification, as you increase the strength of the lenses, you're magnifying the image. Sorry, wait. No, you're demagnifying it. Right? Yeah. So that means we'll have to go in, so we want a really fine probe, so we'll have to kind of go in this direction to increase our spot size in order to further demagnify the source image. And in doing so, you'll see that we're increasing the strength of the C1 lens, leading to a greater and greater demagnification of the source. So as you can see here, so this is just an example from the microscope. So we have a spot size of 11, 10, and 9. And as you can see, as we increase the strength of the as we increase the spot size, we're increasing the strength of our C1 lens. So normally, increasing the spot size by 1 tends to decrease the beam current by half. So ergo, in using a higher spot size to form a better probe, this kind of gives us a more dim beam, or a less bright beam. So it's probably good that you have a fixed source to increase the brightness of your probe, allowing you to get a good signal on your detector. So in this, in terms of talking about like the C1 lens, we changed the C1 lens, the spot size, but you also notice that the C2 and the C3 lens changed, the values changed just a little bit. So from here, like for example, the largest change was the C1, but we can see there's little changes, small changes that were made in the C2 and the C3 lens. So this is just an effect of just how the FEI microscopes are set up. So they kind of use a system which they refer to as a condenser zoom system. So in which the image between the two lenses can be varied. So the image between the two lenses are varied, but the image before, so in front of the first lens, and the image after the second lens, the position remains the same. So in choosing the spot size, in fact, the first step in choosing the spot size, we actually changed all 3 of these lenses, and they work in conjunction so that the image formed after the C3 lens remains fixed. So imagine if you have, a C3 lens down here. As we change C1, the position of the image here didn't change. So the next step here is we need to set up the conditions to form the probe, illuminated area, and the convergence angle. So in the system, we can make the switch between TM and STEM mode, the probe forming. In our particular microscope, so this microscope can be used for TM and STEM. So when you have a microscope like that, normally the probe forming aperture is the C2 aperture. But sometimes, I think in a dedicated STEM microscope, the probe forming aperture would be the objective aperture. So it all just kind of depends on your microscope setup. But the general idea still applies in that setting a larger aperture size will increase your convergence angle, so resulting in a smaller probe size. So here we can, it's just a little example of to show that when you change the aperture size, you'll see a change in your convergence angle. So as you increase your aperture, you're increasing your convergence angle. And then just note that this didn't result in any changes to your lenses. It was strictly an effect from your aperture size. So yeah, as I said, our convergence angle is strictly coming from the probe forming aperture. And here is where we see the C3 lens forms a beam which enters the upper objective lens roughly parallel. So note the convergence angle changes depending on aperture size, and the larger the aperture, we get a larger convergence angle and giving you a finer probe. So you want to choose a convergence angle that minimizes the contribution of spherical aberration. So this is a graph just showing you the contribution of spherical aberration shown in red and the diffraction limitation shown in blue. And so at a small convergence angles, you have a diffraction limited probe. And then at a higher convergence angle, you have a finer probe, but you have increased contribution of spherical aberrations. So we kind of want to choose like a happy medium between these two, and then choose like the right convergence angle for your particular system. Now, the final step in converging is to converge the beam into a probe on the specimen. So we do that by changing the C2 lens and also the resulting C3 lens. As we increase the strength of the C2 lens, there's a further demagnification of the image between the C2 and the C3 lens. So here, shown here. So strengthening of the C2 lens decreases the convergence angle. So as shown here, we have, increasing the strength of the C2 lens will decrease, your convergence angle. And then here we have the same idea in which changing the C2 lens there's also a little change in the strength of the C3 lens. It was adjusted accordingly so that the crossover of the final probe on your specimen, the position remains fixed. And it's also worth noting that when we, at this step, in changing the C2 lens, the strength of the C1 lens didn't change, so the brightness didn't change. That only changes when we choose a spot size. So in the system, the objective lenses are used for optical focusing. So changing the defocus and focusing it on the specimen, the probe on the specimen. So here you'll see that we have a zero defocus in this image. And the probe is focused perfectly on our 1D specimen, which is like this arrow. But in reality, you probably will have some sample with some kind of topology to it, and thus we can use the objective lenses to fine-tune the optical focus. So as we increase the objective lens, we're placing the crossover point to a position that's above our specimen or our arrow, while decreasing our lens will position your crossover points below the specimen. So just a note, adding a little bit of defocus can help compensate for the phase shift in the probe due to spherical aberrations. Um, and this kind of leads us into the discussion of aberration correctors. So much of the resolution in a microscope is generally limited by aberrations in your lenses and the probe forming aperture. So spherical aberration, as you probably already know, arises from the greater demagnification towards the edges of the lens. So here, towards the edges of the lens, you have more of a demagnified image. And so this results in a crossover point on the optical axis that is not located on the image plane. So this kind of results in you get like the spherically aberrated disc, and this can be described by the spherical aberration coefficient CS here. So images, from the Hubble telescope, whenever you talk about spherical aberration, you probably might have seen this image, but they give a beautiful example of the benefits of correcting for aberrations in your lenses. In the microscope, aberration correctors consist of hexapoles and transfer lenses to reduce the spherical coefficient, so thus improving the resolution of our probe. And we normally, or not we, but the correctors are normally placed between the objective lens and your see-through lens or your condenser lenses. So here in our facility, we have these CS aberration correctors. So it is, while it's still possible to obtain atomic images without correctors, we can kind of see, the benefits of aberration correction. So with a smaller probe, we can see with a smaller probe formed from the correctors, you can see that the contrast is brighter in the image as compared to the uncorrected image. Correctors also provide an advantage in that they form a brighter probe due to the fact that the probe is smaller. So this means that we can increase scattering in our sample and therefore increase the signal that we collect, giving us a better signal to noise ratio. All right, so that kind of like was a brief kind of discussion of forming a really nice probe. Obviously, there's a lot more that goes into it, but now we can kind of go into the detector. So once you once you form like a nice probe, you'll need to adjust your detector so that you're collecting the right and collecting at the right angle. And you want to collect these these electrons that were scattered to a high angle. So you do that by changing the camera length. So i.e. you are just changing the distance between the detector and your sample. So in our system, it's basically just done by the click of a button in the upwards or the downward direction. A long camera length would result in a smaller collection angle, in which you could probably collect incoherent and coherently scattered electrons. Shown here. So here we have like our inner and outer angle. But as you decrease the camera length, you can increase the collection angle and collect these high angle scattered electrons of interest, giving you your Z contrast image. There are references out there that have simulated the scattering cross-section, which you can use to determine the collection angle for your detector, and what kind of collection angle that you need for your particular sample. But it's a general rule of thumb that you probably just adjust your camera length to have an inner collection angle of at least 50 millirads, if not greater. So it's good to note that from this you can kind of get quantitative information from these images. You want to quantify the amount of atoms that you see in a column using the intensity from your images. In reality, it's just kind of difficult to do. It requires, you need to simulate the image that you'll see. You'll need to calibrate your detector to measure the dose. And also, you'll have to think about your sample. It's subject to surface contamination and things of that nature. And so generally, we kind of take a more qualitative approach in which you like to confirm, whether your sample contains certain elements of or layers of interest. So in this case, we can combine imaging with spectroscopy, sorry, to give you that kind of information. And one advantage over TEM, I don't know if I said this already, but is that you have the option to acquire dark field and bright field images at the same time, or in this case, you can also collect, high angle and medium angle scattered electrons and create these kinds of images. So as you can see here, the contrast in the Hadoop signal is, easily interpreted in terms of mass thickness of the material. But in here, where we collect a little bit more coherently scattered electrons, we can see a little bit of diffraction contrast in this image when it's collected at larger camera lengths. So I don't know, it's kind of like a benefit. I mean, you can collect both of these images just from one scan. Another important thing that you're going to want to think about is the position of, or the tilt of your sample. So in acquiring atomic images, it's important to align the crystal to this, in which the zone axis is parallel to the beam. So by doing so, we get what we call channeling conditions. This is where the fast negatively charged electrons are kind of attracted to the positive atomic nucleus in the column. And so it kind of channels it, kind of focuses the probe of electrons to exactly where the scattering occurs. And this, by doing so, we get less beam spreading or broadening of your beam as it travels through your sample. It's important to note that the strongest contribution comes mostly from the atoms position closest to the beam, so say these atoms here. And then as the beam or the probe travels, the electrons travel through your sample, the probe is just depleted, and then when it reaches the atoms in the lower column, it's kind of scattered in different directions. So therefore, if you have a thick sample or a region where it's a little off axis, you'll see some kind of background contribution between the column of atoms. So here, kind of showed here, you have a little part of this sample is a little bit off axis, and so you kind of see more background as opposed to this region of the sample where you have a good on axis orientation, so you get a good contrast. What is unique to imaging with a probe, which is also with SEM, is that magnification results from the area of scanning that is performed on your sample. So magnification is calculated by taking the area of your frame size. So say you have a 2048 by 2048 frame, and you divide that by the sample area that is actually scanned. So that means if you scan on a smaller area on your sample and you have the same frame size, then you're increasing the magnification of your image. So note as we went from 640 to 2.5 million magnification, there were no changes made in the lenses. The magnification purely just arose from scanning area on your sample. And then you're gonna have to, when you're choosing this, you're kind of gonna think about what is your sampling frequency. And so it's a general rule of thumb that you're kind of going to want to have your pixels of a size that's at least, not at least, but more than double than that of your object of interest. So this means that if you want to have, lattice spacing in your images, or you need to know the kind of have an idea of the object, the size of your object of interest, and then you just adjust your parameters accordingly so that your pixel size is more than double of this size. So it's always good to kind of oversample your image, but this kind of comes at the cost of time. And so this could be precious depending on the robustness of the feature you're just capturing. So for example, if you are scanning, if you're scanning, it's going to be like, takes longer, then it's just going to kind of destroy your sample, which is like kind of, I guess I should have discussed it here, but in this window you also choose the scanning rate or the dwell time of your image. So the dwell time is the time that the probe is in a fixed position in order to collect data for 1 pixel. And so the total frame time is the total number of pixels multiplied by the dwell time for each pixel, and that gives you your total frame time. So that means like the time required to acquire your image. So if you have a shorter dwell time, you'll be able to collect an image faster. But then this comes at the cost of decreasing the amount of signal that's collected onto your detector. Additionally, the acquisition of your image runs top down, so it scans from left to right and from top to the bottom. And so that means that you're not acquiring a static image, but rather you're acquiring an image generated over a given amount of time. And so that kind of means like the regions at the bottom of your frame was acquired at a fraction later than what was acquired at the top. So you can the most apparent artifact that you could see in your image is sample drift. So this is just an example. If you're a little impatient, I can be a little impatient sometimes. You don't let the sample settle on the microscope and you try to acquire an image. This is what you actually get. And you can see that the stage or your sample was drifting in this direction, and you can kind of see that in your FFT. So note that the stretching is not from astigmatism, but it actually is from sample drift. And here we have a more representative sample in which you wait a little bit more and then you acquire your image. So you have to kind of play around with your magnification and your dwell time to figure out the right imaging conditions. And the fastest way I would say is to test this is just to test it in your session and see what kind of images that you get. So, but you'll have to think about like there's potential to damage your sample while you're testing these parameters. So it's good to either have a test sample at first, or maybe have a large sample area so that you can test these parameters in regions that of not interest to you before taking a final perfect image. So some other artifacts that you could see in STEM images. So some are that due to the fact that we have a probe, you're subjecting a relatively large amount of energy into a small area. So you can have beam-induced contamination on your sample, or actually create a hole in your sample. So here we kind of see a buildup of carbon layer in our sample. If we continue to collect, multiple frames or multiple images, we would actually see the thickness of this carbon layer increase, so just get thicker and thicker. This carbon layer obviously decreases your signal to noise ratio, and it doesn't give you good imaging. And also, if you're working with a sensitive sample, sometimes holes can be formed within just a few seconds, or if not even sooner. So you'll have to like take that into account. Like this hole isn't a good representative image of your sample. So say you did acquire a really nice image, you can do some processing up to that image. So you can kind of get rid of some noise that you have by applying some Fourier masks. And here we got rid of some noise in this image here. Applied a mask, and we kind of get a nice, nicer image. But some care must be taken in order to not remove or add any false information to your image. So another promotion, there was a nice talk about this. You can find it on our YouTube as well. It goes more in depth about image acquisition and processing. And so lastly, it's also important to put some care into preparing a good sample for your microscope session. So a well-prepared sample results in good data. It's not always the case that you can pop your sample into the microscope and obtain, publishable results. So in general, you kind of want to make sure that you have a good representative sample. Our field of view in the team is quite small relative to what you would see in SCM, or definitely up to like the optical microscope field of views. So you want to make sure that you're looking, what you're really looking at is a good representation of your sample. And since we're collecting transmitted electrons, you'll need to make sure that you have a nice thin sample. Generally, the thinner the better. If you have a thick sample, you won't be able to, get good signal from it. You also have to kind of think about all these other things, of your sample, whether it's stable under the vacuum or the probe. Is it free of contamination? This is kind of hard to do, but there are, you can do some plasma cleaning or use, really pure solvents to make sure that you can to reduce contamination as much as possible. You want to make sure that well, it depends on what kind of, analysis that you're trying to do, but you kind of want to make sure that you have a uniform thickness in terms of, when you're trying to obtain atomic resolution images. And then you're gonna want to consider whether your sample is conductive, or will it just kind of, acquire all these electrons and resulting in damaging of your sample. All right, so in summary, Z contrast images arise from incoherently scattered electrons, giving us our Z contrast images. We mostly or commonly use them in conjunction with EOS or EDS spectroscopy. You can tune the condenser lens system and give you a really small coherent probe. And then you're also going to want to tune the camera length to adjust the collection angle that's appropriate for scattered signals of interest. And you're going to want to think about, acquiring and interpreting these images. What do you need to do to get good data or useful information from this? So it's very important to, invest time in sample preparation and experimental setup. So in summary, I hope this helps you in preparation for your next session on the microscope when the facility opens up to users. I'm not sure when that will be yet, but hopefully soon. You can start preparation of your experiment, now, and think of all the parameters that you'll need to come up with a good game plan so that you have a really good session when we return from quarantine. And then a little, reminder, tune in next week for sample prep information. So next week, Friday, at 11 a.m., the same time here. So I'd like to thank you for your attention and attending this webinar. I will be happy to ask any other, or answer, sorry, answer any other questions that you may have.
Okay, so there's a few questions that came in, and if any of you have questions based on the talk or based on what happens here, can you please just put your questions here in the chat box. So Natalie, one question. Once you set the eccentric height in TEM mode, should it again be adjusted when switching to STEM mode?
Yeah, I would think so. I can't remember. I think so, yeah.
Okay.
Should. Probably should.
Um,
I can't remember right now.
Natalie, did you image any biological samples in the Titan? Do you think it's possible?
I have not per se using STEM, but I have done so for T. STEM is a little bit harder in that, your sample damages a lot more quickly, but we have a direct electron detector, so that really helps us acquire fast images to our sensitive samples. So, for STEM, no, I definitely want to try it out one day. Gonna work on it, but for TM, yes.
Okay. When you change the objective lens by changing the focus in FEI TEMs, does that slightly change the convergence angle as well, even though you're not changing the C2 strength?
No.
Okay, so if not, which apparently it sounds like it is, where does the defocus change actually, what is changing the defocus doing in your dark field STEM images?
What is change? So it just changes like the position of your probe, but you're not actually changing the convergence angle. You're just changing the position. If that makes sense. Of,
Yes.
yeah, the probe on your sample. You're just changing like the position of it, but you're not changing the angle. I believe
Okay.
that's right.
How is channeling affecting the contrast in STEM?
So it kind of just it really kind of like say it's a kind of like a magnet, like it just attracts those electrons to the column of atoms, and so you can get a lot more scattering. And so like say if you don't have channeling, the electrons are go into your sample and they're just scattered, and that's why you can't really see any lattice imaging in STEM, is because they're just scattered all over throughout your sample. But the tilting it to zone axis really helps you like accentuate, I guess, or the it really focuses like these electrons, the probe electrons, in a specific area rather than be scattered throughout your sample.
Okay. What is the difference between bright field and annular bright fields in STEM?
So you kind of get the same image. It's a coherent image. You can see, diffraction contrast. But I think the main kind of advantage is that since you're using a probe, um, you also, as I said, you're not subjecting like your images to aberrations from your lenses. So if you have a nice probe, you can kind of get a nicer image. But I guess it just all kind of depends on what you kind of want to get from it. But there is an advantage that you can, acquire bright field and dark field images using like these annular detectors. So you can acquire them at the same time. And so like as opposed to TM, if you want to acquire, a dark field image, you have to switch it, select, your diffraction spot, and then, you can acquire a bright field and dark field image at the same time. I think that was the question. I don't quite remember.
Okay, we'll do one more question and then any more questions that come in and any remaining questions we will answer later on and we will post it to the YouTube channel. So what kind of TEM holders, grids, or substrates are available for imaging soft materials? Carbon grids, perhaps?
Mm-hmm. Um, yeah, yeah. Carbon and holders. I mean, we have a cryo holder. So say, you have soft samples it's gonna damage under the beam. We have a cryo holder so you can kind of cool it down so you can reduce, the damage done to your sample. I would probably just use a cryo stage or a cryo holder. Sorry, not a cryo stage, a cryo holder. But yeah, you can also, I guess, use, you could probably just test it out. You know, it's quicker to do it that way. Just kind of do a quick test and see how your sample behaves at room temperature. Because using a cryo holder, it takes a lot of time. You have to cool it down. Like you have to wait for it to stop drifting. So it can take a lot more time to acquire an image. You also, can only probably image, one or two samples a day, maybe even two. It just takes a long time. So it's good to kind of just test it out first before you actually do cryo, I would say, if you don't know anything about the sample.